scheme. Okay. Again, I don't have the chat open, so if you have a question, just unmute yourself and ask it. As a lead-in to today's lecture, this was a slide from the previous lecture, and yeah, this is yeah, we can ditch the Santa hat. Okay. And in order to detect corrupted messages, we generally add some sort of frame check, some sort of check here at the end to answer the question, do I have all the bits correctly? Now, remember, in terms of this context, the size of this message can be fairly large. Okay, so there is no register on any processor that's going to hold 18,000 bits at one time. Okay, so that will be a constraint in developing these things. Okay, so that's our lead in for today, and is to talk about the other sort of revelation that I had about this is I haven't done this since I was your age, by the way. I took a class from Ron Rivest at MIT when I was a grad student, where this syntax was developed. And since I went into biomedical instrumentation, that was the last I heard of it until designing this class. So it was kind of a historical fun to go back and revisit some of the math that I learned as a grad student taking an algorithms class. Ron Rivest went on to design some really cool encryption and communication protocols. But he was a young thing. I got him as a grad. Rivest. Yeah, you can Google him. I got him as a fresh assistant professor when I was at MIT. And, I think those of you that have come to office hours and ask questions in class, I'm always asking the question why and what, and, how could we do things differently, and how could we make it worse, right? I mean, that's generally I'm an agent of chaos. And it was fun to see that chaos is actually a parameter in this method. Okay, these are the 3 websites that I use to accumulate the stuff for this particular lecture. Now, one of them refers to the Tannenbaum book, which I did not refer to. Yeah, but as you can see, yeah, it's dated when I was a grad student, so that's how old this stuff is. Okay. All right, so what we're going to do here basically is error detection. Okay, this will be our method. We're trying to receive a packet and decide yes or no, is it correct? Okay, that's our essential goal. And along the way, we're going to do 2 very simple protocols, 2 simple methods that you probably heard of before. But we'll focus most of today talking about this cyclic redundancy check or code. We'll begin with a definition of distance. And I'll say it right up front. There are two main sort of parameters or categories or ways to describe these methods that will differentiate between good ones and bad ones. Okay, the first is width. Okay, so in other words, if we have a message, okay, and we add some bits to it, okay, the number of bits we've added is the width. Okay, and as you might imagine, the more bits I add, the better the chance is that I will detect an error if there is one. Okay, so a failure is defined to be an error occurs, but it's undetected. Okay, so 2 bits got flipped and the checksum came out right. Okay, that can happen. Okay, and then another one which is a little less obvious. Okay, And that is, if you go back to this model of, of, of message and width, okay, and you take one bit out of here, just one bit, okay, and then you ask the question, what is the effect of this one bit on these bits, right? What's the effect? Is there any correlation between this one bit I here, right, which is in the message, and these bits there, okay? And so chaos is a characteristic that says that any information in here can cause a potential change in the register. Okay, so is each of these bits here not necessarily equally dependent on, but is it dependent on the other bits, on this one bit? Okay, and so if the data here, if one of these J bits in the checksum, okay, in the thing I'm going to send at the end, if it's dependent on lots of bits, or conversely on all the bits, then it's more chaotic. Okay, and we will see that the actual motivation for CRC is to increase the chaos, to allow to drop the probability of a failure, to increase the probability of detecting an error. Okay, so so the each input information has the potential to change any of the bits in the register. Okay, obviously, you remember this was, this was, this was a big number, right? That was a lot of bits, and this may only be, there may be thousands of bits here, and 32 bits in the W. So obviously, it's a weak correlation. You can't reverse. It's not a this encryption. I mean, not encryption. This checksum is a one-way function. Obviously, it goes from M bits in the message to W bits in the checksum. That's a one-way. It's not a reversible inverted function. But the point of chaos is to let each bit in the checksum be dependent somehow on as many bits in the message as possible. Okay, and that will increase our probability or decrease our probability of failure. Okay, or increase our probability of detection. All right, so one of the ways we look at the goodness of an algorithm is something called Hamming distance. Okay, and we'll see this way at the end of the lecture. Okay, and that is now Hamming may have described it as characters like letters in the alphabet, but we're going to use, we're going to say, when we use symbols here in this context, we're going to mean bits in our message. So, for example, this one, you can sort of see it graph. You can either see it with a graph or with a sort of math. Okay. If I wanted to convert the 4 into a 9, so the question is, how far away is a 4 and a 9 from each other? Okay. What kind of noise would I have to introduce to this system to convert a 4 to a 9? All right, that was a question.
3 bits.
I have to flip 3 bits. I have to flip this one. All right, I got to flip that one and that one. So I got to XOR. I got to flip 3 bits. And so we're going to define as these two symbols in our space to have a Hamming distance of 3. Okay. Whereas if I were to convert a 6 to a 14, okay, a 6 and a 14 are very close to each other in the physical space. Okay, this particular drawing that I stole off of Wikipedia draws a 4-dimensional space. Okay, and to go from a 6 to a 14 is only a 1-bit change. Okay, so these two numbers here are very close, and these two numbers are very far when it comes to Hamming distance. Okay? So if I've got 100,000 bits in my message, I have 100,000 dimension space. And now the question is, can I add bits to my, can I add noise bits to my communication such that I end up with another valid, but a valid checksum, but an invalid message. Okay, so that's the way in which this is used. Okay, so we'll see Hamming distance when we get all the way to the end. Okay, all right. So this is a stupid one, and that is if I do just do a mathematical sum. Okay, so I take my message. I got capital N characters, right? And these are bytes, right? So this is these are bytes, 8-bit bytes, and I just add them up modulo 256. Basically, I just take the bottom 8 bits of the sum, and that is my checksum. That's the derivation, actually, of the word checksum, and we use the sum to check. Okay, now we use the sum to check. The word checksum will persist beyond the actual operation of sum and be used for all sorts of things, including CRC. Okay, so be careful when you see the word checksum in a context. Make sure you find out how it's defined, because sometimes they'll mean this very simple method of where you add it up, and sometimes they'll mean something totally different. Okay, and so what we we adding 1 byte. Okay, so this is a n byte message. We're going to send n plus 1 bytes, and the sum will be checked on the receiver. Okay, now Hamming distance can be okay. So if I have a message, right? Let me just do a simple message. I send and I'll do it in 4-bit mode because the math is easier for me. Okay, I have n equals 3. All right, so I'm going to add these up. Right, so that will be a 0. Carry the 1. That is a 1. There's only 1 there. Carry the 0. Okay, so I'm going to send that checksum. Right, that checksum here. I did the math right. Okay. So what would have to change? Can you give me an example? This is a correct answer, but what bits might change that cause it goes as an undetected error? So let me ask an easier question. If I were to change any, I have 4, right? I have 4 characters, right? I have a 9, I have a 12, I have a 1, and I have a 6, right? That's my message. If I were to change any 1 bit, right? This is a 4 times 4, 16-bit, a 16-bit total message. If I were to change any of those 16 bits, would it be detectable? Right? Think of this as a 16-bit number. If I were to pick any bit in there, and if I were to change it, would it be detectable?
Yes.
Yeah, sure. Because the only way for it to be undetectable is if I change 2 bits. And where, if I change 2 bits, I can go from, if I change 2 bits, obviously it's an error, but I can have the correct checksum. Okay, so for example, if I just swap the bits here, if I go 0, 0, 0, 0, I just swap that bit and this bit, right? And then leave the other 2. Right? I just swap those 2 bits. I flip both of those bits. The checksum will come out right. Okay. Now, this is not to say that this code can detect all one bit errors is correct, but it's not in some 2-bit errors. It's really not the answer to the story. Really, what I want to know is, given a random number of corruptions, what's the chance they won't be detected? And I don't know that I did not find the math on this, but I copied it out of the the first article. I copied it at no, this one in bar. Which probably copied it out of the other one, but it was a chance of 1 in 256 that there's any number of bits that gets selected. In other words, whatever this number is, I can improve it by increasing the width. Okay, so if I change the width from 8 to 16, I will reduce the probability of failure. Okay, that's sort of the message here. But the problem is this bit here, right? This bit in the message is only affects that bit in the checksum. Okay, in other words, it's not chaotic. There's no twangling of the bits such that information in this particular bit propagates to multiple places. And similarly, this bit here can only affect that bit. Okay? So the point is, it's not very chaotic, and therefore the Hamming distances are not very good, and the chances of detection are not good, or not as good as they could be. If I gave you an 8-bit number, you could do better, I guess is the point. All right. Let me do another one, which is sort of easy to explain, but also not very chaotic, but it's easy to explain. It's got a name. It's called either horizontal parity or longitudinal redundancy check. Rather than add the bits, I'm going to XOR them. This is even less chaotic because there's no rolling of one bit into another, right? So this is actually worse than the other one because the lower bits can propagate into the higher bits, but with a low probability. But here, bit number 5 in the message can only affect bit number 5 in the checksum or in the whatever we're going to send. Okay, so again, assuming here that the message is a byte, and this n is also a byte, we will send n plus 1 bytes, including this longitudinal redundancy check. Okay, again, it's there are plenty of codes which are very close to each other. That 2 bits Hamming distance here is again it's got a minimum of 2. So there are some 2-bit errors that will go undetectable. The fun thing about this one is if you were to combine horizontal parity with vertical parity, you can do something cool. So here's an example. I'm going to send the letters capital C, little I, capital A, little O. All right, I'm going to send these characters. All right, so that is a 1, 2, 3, 4, 32-bit message. Okay, and I am going to convert that, okay, into a, okay, so it's this was 4 times 8. I'm going to convert it into a 5 times 9, into a 45-bit message. Okay, and you'll see what I do here in a moment. So here are the letters sort of in matrix form. Okay, see that? There's the right. This one here is the 43. Okay. Okay, and there's the 6F. 6-1, 6-9. Okay. So I'm going to visualize this in 2 dimensions. I did that. Okay. And now what I'm going to do is I'm going to add a horizontal parity. In other words, this bit here is equal to the exclusive OR of these bits. Okay. That's what we talked about before. But in addition to the longitudinal redundancy check, I'm going to add a parity bit so that if I exclusive OR these bits, I don't know if it makes sense, you know what I'm doing to get that bit. So I'm going to exclusive OR each of the bytes to get a parity bit. So that's where I got the, I went from, like I said, 4 times 8 bits up to 5 times 9 bits. So I went from 32 bits up to 45 bits. I added 13 bits to this system, okay? In all of these protocols, there is, if I send this 45 bits, how do I tell if there's an error? What's my error detection algorithm in this protocol?
You just compute the parity the same way and see if it matches.
I'm going to have to do, right? If you think about it, I'm going to have to do 1, 2, 3, 4, 5, 6, 7, 8, well, 7 exclusive ORs, okay, for the bytes to get the parity bit, and then n exclusive ORs in this direction. Right, so I'm going to do a lot of exclusive ORing. Okay, now luckily for us, this is typically built into hardware, and so the parity bits are generated in the transmitter and checked in the receiver. Okay, and then I'm going to then make sure that the exclusive OR of this actually equals that, and the exclusive OR of this actually equals that. Okay, but let me. Okay, so I'm going to quit this so I can get a fresh thing. Okay, something fun that can happen. Somebody pick me a bit. Give me a row number and a column number. 1 bit.
70.
Okay, 7. That one. That the one you meant?
Yeah.
Okay, let's flip it. Okay, what are the consequences of that 1 bit being flipped? Right? This is going to be wrong. Are we right? Because 1, 1, 1, 1. Well, it should have been a parity of 0. It's going to be wrong. Okay, where's the other mistake? Where's the other detection? Which other one is going to show up as an error?
The across.
Yeah, right there. That will be an error too. Okay, so I flipped 1 bit and got 2 errors. You see that? So it was detectable. But there's something cool you can do here. What can I do? I can correct it. Okay, and so it's a mathematical sort of field that is really not, as far as I can see, used a lot in IoT. But one of the things you can do, remember we took n bits of message, we added w bits of things, and the basic method or objective of the whole lecture was to detect an error, right? The noise flips the bits and you're trying to detect it. But there's a whole mathematical field that can I correct it? These are called error correcting codes. which in a way, so you can sort of I don't know, I'm not very good at drawing it, 10,000 dimensional space, but let me give you the basic approach here. All right, so if you have a message here, okay, in 10,000 dimensional space, right? And one of the hallmarks of a good protocol, a good checksum space, is to think about the minimum Hamming distance. Okay, so if we take all 10 billion or 10 trillion or 10 gajillion possible messages and draw it in a 10,000 dimensional space, and we looked at the valid messages, okay, in that space, then if I receive this message, what are you going to do with it? It's not, it's not one of the valid messages, so it's wrong. But if I calculated the Hamming distance from M received to all of the potential messages, okay, and I saw that D1 was less than D2, which was less than D3, which was less than D4, okay, what would you do? I received MR, and I noticed this relationship, right? Distance was how many bits had to flip in order for you to convert one message into another.
I guess I'd assume that the one with the shortest distance is probably.
So I'm going to convert, I'm going to correct into M1. And am I going to be correct all the time? No, because it actually could have been M2 or M3, but chances are it's more likely to have been M1, right? So, if it smells like an elephant, it looks like an elephant, tastes like an elephant, it's probably an elephant, okay? That's the essence of correcting codes. Okay, enough of that. All right, so now, okay, so here I plan to do this. I don't know if this is going to work or not. Okay, so quit this. All right, because I'm going to type. All right, so I'm going to do something that you probably already know. Okay, so I'm going to do a 8-bit by 4-bit division with regular binary math. Okay. All right, so tell me if this is boring. Okay.
Wait, I have a question.
Yeah, go ahead. Yeah.
So, if you had several shortest distances, do you check each one and then recompute this checksum?
Oh yeah, no, this is probably why it's not used, is because it's computationally horrendous, right? Because think of the space that I have to do, right? Remember that if I have a 10,000 byte bit message, okay, that means I have 2 to the 10,000th possible messages. Yeah, so you're going to have to commute the smallest distance to all of these. This is why we don't do it. It's computationally outrageous. Right? In my case, I only had 4 messages. So in And this includes this includes the plus W, right? This is, so let me just, if I have a 4-bit message in a 4-bit, W checksum. Okay. That's 2 to the 8th. Now that's probably, now I've got only 16 possible messages. Okay. And so I probably could correct for it. Yeah, so it just probably only works when the numbers are really tiny. Right, so in this context here, if I have a 4-bit message, there are only, now my dimension, it's an 8-dimension space. It's an 8-dimension space, but there are only 16 messages. So now when I receive a number, I have to check. Now, maybe there's a better way to do it. And that's, this is the only error correcting code that I've understood. And so, yeah, you want to, if you have 16 possible messages and you get M sub R, which is any 8-bit number, what you want to do, obviously, to get this W, you want to spread these 16 messages in 8D space far away from each other according to Hammond distance. Did I just make it more confusing to you? All right, having allowed myself to confuse you. I mean, I'm going to have to type this. I'm going to do regular division. So what I'm going to do is I'm going to compare, right, these 4 bits with that 4 bits and decide to put a 0 right here, okay, because this number is bigger than that number, right? The 9 is bigger than a 6, so I'm going to subtract off a 0, okay, and get the same thing, obviously. But now I'm going to compare this number. I get rid of that one. I don't need that one anymore. All right. Okay. Every time I go down here, I lose a bit. I'm going to compare this number to that number. And 12 is bigger than 9. So I'm going to take a bit here. Right. So this is the binary. This is division, which is successive subtraction. Shift, compare, subtract if bigger, right? That's the essence of subtraction. Okay, so now this is binary subtraction. So I got to go, subtract that. Okay. Okay, so I'm losing a bit. I mean, every time I go here, it goes smaller. Okay, so I got to carry, I got to borrow. So, okay, so that's obviously, that's easy for me. That's 12 minus 9. That's going to be 3. Okay. All right. And then carry the other 3. All right. Did I do that right? Again, I'm going to lose a bit. So I'm going to throw that one away. All right. Every time I go through here, I'm guaranteed to make the number 1 bit smaller. Okay. So this is the, there's the, the dividend, which is decreasing in size as I sequentially subtract from it. And now when I compare, this is a 7, I compare that to a 9, I'm not going to subtract anything off. Right, because it's bigger, and so I'm going to keep this. Again, every time I go through, I'm losing a bit. Okay, let me see if I got the answer. All right, this one is bigger. 15 is bigger than 9. So I'm going to take myself a quotient here. It turns out the quotient is going to be relevant. I got to end up with 11. So far it looks good, right? Looks like it's going to be an 11. Okay. Subtract 0, borrow, that'll borrow, so that's a 0. No, yeah, subtract. Okay, so what I was 15 minus 9 is going to be 6, right? So that's going to be. Let's see. I better end up with an 11 with a remainder of 4. Okay, okay. So again, you keep the other one down. Okay, so yeah, that's a 13. I'm in good shape. Okay, so one more. 13 is bigger than 9, so I'm going to subtract this guy. Stop. And again, every time through, I drop a bit. Okay, so that's a 13, that's a 9, and there's my 4. Good. Good shape. Okay. So that was a big fuss to take 103, divide by 9 in integer mode, get a quotient of 11 and a remainder of 4. Okay. But what you had to remember is what I did at each stage. I did a shift and then I did a comparison, right? I compared the divisor with the dividend, with the shifted divisor, or the shifted dividend. You can do it either way. And then if the dividend were larger than the divisor, then I added the quotient bit was on and I subtracted the divisor. Okay, that's binary division. Okay, so and let's see if I got the, yeah, so I go to the next slide. Okay, yeah. Okay, so I worked it out in advance just to make sure. I know this one's right. The other one, I don't know. Yeah, fine. I could have. Okay. The interesting part here is I'm going to take the remainder. Okay, the 4. That's the cool part. Okay, that's the cool part, and I am going to grab hold of it as a valuable information. Okay, so basically, the method. Now this is binary division. We're going to invent our own math here in a second, but basically we're going to define this as this 9 right here. We're going to define this as as what's called a poly or polynomial, and this is going to be our CRC. But we're not going to use binary division. Okay, we're gonna throw this part away. This part's irrelevant. Okay. The cool part about division, it's very chaotic. Okay, it is very chaotic because all the bits interact with all the remainder of a division is a function of all the bits everywhere. Okay, that's why this thing is appropriate. Okay, so enough about binary division. We're going to do polynomial division, and this is the part that I remember from my grad school days. That was I was completely fascinated by it. At the time, I had no idea why it was important, but it was sort of fun just in itself. Okay, so we're going to develop a mathematical, a new number math. Okay, and so now when I'm going to take numbers, right, I'm going to take the number 23, a binary number. I'm going to take this number 23. Yeah, so I'm going to take this number 23, or this in hex. So this is obviously hex here. Okay, and I'm going to make a correspondence with the binary bits to be coefficients of this polynomial function. So this is called a polynomial or a poly here. Okay, and if there's a 1 in the binary, there's going to be an existence of these polynomial devices. And the key here is the coefficients of any polynomial, all right, is going to be a binary number where this b can only be 0 or 1, okay? And we're not going to carry, okay? There's no carrying, okay? So let me just do an example of polynomial math here. Again, this is in hex, right? So this is a 1 0 1 1 1, okay? Because there's no bit 3. And this is a 0 0, where'd it go? Oh, 0 0 1 0, okay? So I'm going to add hexadecimal 17 with hexadecimal 5, okay? And I'm going to get 18, okay? Just warning you. 17 plus 5 is going to be 18, okay? And it's going to bother you because it bothered me when I first saw it, okay? And so if you just take the polynomials here and just do the regular add, okay? You get 2 of those and 2 of those, right? There's 2 x2s, there's 2 x0s and 2 x2s. But since you can't represent 2, we're not going to carry it into the 3, okay? The 2 x to the 2 is not equal to x to the 3, okay? X is not 2, okay? Now, x is not 2. Don't think of x as 2. Don't think of it as anything, okay? It doesn't make sense that if x is 1 or 12 or pi, it's just x, okay? And so we're going to toss this out because when I add 1 plus 1 in binary math mod 2, 1 plus 1 is 0, okay? A 2 is converted to a 0. And so I'm going to get that polynomial. Interesting, okay, is we'll subtract those exact same 2 numbers, okay? So there's the 17 again, right? 1 0 1 1 1 and a 0 0 1 0 1. I'm going to take 17 minus 5. Again, that's x 17. And I'm going to get the exact same thing. So 17 plus 5 is actually equal to 17 minus 5. And what's up with that? Is that actually a true statement? It turns out it is, and it is kind of a fun thing. Another one that's kind of interesting and important is if I add a 0, right? A 0, if I take the number 0, the polynomial I get is blank, right? Nothing. There's no x's at all in it, okay? Because x bracket 0, right? That polynomial is a 0 0 0 1, right? Or whatever, okay? But if I want a 0, I have all the coefficients are 0, and therefore I have a blank. So if you add a blank to a polynomial, you'll get back that same polynomial. Similarly, if you subtract a blank, the other one works too. Yeah, it's multiply is a little bit fun, but again, very straightforward, because now I'm going to multiply 17. That's hex 17 times 5. And there's the 17 again. There's the 5. And so now we're going to do, we're going to do 9th grade math, right? We're going to do algebra math on the terms, but then we're going to do modulo 2 arithmetic on the coefficients. All right, so there's one x6 term, which is that one times that one. It turns out there were 2 x to the 4th terms, right? 4 times 0, and 2 times 2 gives me 2 x4 terms. But I'm going to, since there's a 2, I'm going to throw it out. Okay, and so there's 2 x2 terms as well. I'll throw it out. Now, if I were to have a 3, again, so a 0 goes to a 0, a 1 goes to a 1. In modulo 2, a 2 goes to a 0. But what would 3 go to? If I had a 3, this one didn't have one, but other examples, I might have I might have a term 3x to the whatever term 7 or whatever. What would I do with a 3?
Would it become 1x?
Would become a 1 because it's modulo 2, right? So in my modulo arithmetic, 0 to 0, 1 to 1, 2 to 0, and 3, where'd it go? It's gone. It don't matter. 3 goes to a 1. Okay. And that's how I multiply. Okay. All right. To do division, you remember there were 2 steps in division. Okay. Okay. Here's a general slide. Sorry, I forgot. One more slide. Again, we're going to do a mapping between binary numbers. Okay. And the polynomial associated with it. So this and that are symmetric, amorphic, there's symmetry. There's no more, no less information on the left and the right. Okay. So they're just different ways to represent the same thing. Okay. An interesting, okay, yeah, that's another coming up. Okay. Again, polymath is modulo 2 and not, not with no carry. And so we saw in the previous slide, when 0 plus 0 is 0, which is still 0, 0 plus 1 is 1, still 1, 1 plus 0 is 0. But 1 plus 1 is 2, which gets morphed back into 0 without a carry. Similarly, 0 minus 0 is a 0, 0 minus 1 is minus 1, which gets modulo 2'd back to 1. Okay. 0 minus 0 is a 1, and 1 minus 1 is a 0. And from this assignment, you can see that there is a corresponding behavior here that lets you to prove that A minus B is identical to A plus B. Okay.
So I have a question along the same line. Does that mean that A plus A is 0?
Thinking. Yes. Sure. Because A plus A is either this one or that one, right? And, or, yeah, sure, absolutely. A plus A would be 0.
That's weird.
Yeah, it's way weird, but it's fun. I don't know if it's fun or not. It's an algebra. I don't know if you've got enjoyed that kind of math, but there's all sorts of other things you can prove. A plus B is equal to B plus A. A plus B plus C is equal to B plus A plus, you can group them anyway. It's associative, and I don't have associative. I don't know about associative. I gotta, but it's symmetric. All right, so addition is the same thing as subtraction. Okay, so we don't need another formula. Okay, and okay, well, duh. What function is that, by the way? What actual function is this?
Isn't it just an XORing of every single?
Yeah, this is just XOR. So, and when it goes to be implemented, this is an exclusive OR. Okay, so add and subtract are basically exclusive ORs. Okay. Now multiply is not, and division is certainly not, and that's where we're going. We need division. Okay. So this is, if you like, a whole new mathematical, the one of the authors calls it polymath, invented by this guy in 1961, for the purpose of making a check code which is very chaotic. Okay. All right. Okay, this is multiply. Okay, so we'll get into division in a moment. Multiply, if we wanted to implement multiply, in polymath, it is like regular multiply. So if I'm going to, so here you see this guy is repeated here, here, and there, okay? And then we are going to add, because of that one, no, that's this one actually. We're going to, okay, we'll call that add 0. We're going to add 1 because of that one. And we're going to add 3 because of that one. So again, it's a shift and add, but remember that you don't do any carrying, okay? So we're going to shift an exclusive OR, okay? So we got 2, and so again, this is now decimal, okay? There's 13, which is, you know, obviously 8 plus 4 plus 1. There's 11, which is 8 plus 2 plus 1. 13 times 11 is going to be 127. Okay, I mean, it's a weird math, but it's a math and it's perfectly well defined. Okay. But we're going to implement multiply as a shift and exclusive OR, if you'd like. We're going to do a shift and then do a poly add, which is a shift and exclusive OR. Right. And obviously I didn't add a 2 because that bit was a 0. Okay, so that was multiplication. Now to do division, we have to know whether to subtract or not, okay? So when you divide, you shift over the divisor and compare it to the dividend and you say, should I subtract or not, okay? And these are not provable. I couldn't figure out a way to prove that this polynomial, this poly is bigger than that poly, because if you actually plug in actual x's, in other words, if you plug in x equals 1, I tried it, it didn't work. If I were to plug in x equals 1, I get 6 is not greater than, okay, no, x equal, oh no, sorry. If I plug in x equals 1, I get 2 is not greater than 3, sorry. So if x equals 1, this thing calculates to be a 2, that's a 3, and that's not true. Okay. If I plug in x equals 2, then it is, okay. But so this is, don't try to prove this with x equals some number. Okay, so again, x is not a number. It's not 2, it's not 1, it's not nothing. Okay, so this is actually a definition. Okay, and so we will claim that one poly is bigger than another poly if the coefficient of the largest term is bigger than the coefficient of the other largest term. And that's because it's bigger because 5 is greater than 4. Okay? And so when we compare two polynomials to see which is bigger, we're only going to look at the most significant bits, the term with the highest non-zero coefficient. Okay? Whereas if we were to compare these two, okay, we're going to call them the same size. Okay. So a polynomial can either be bigger, less than, or equal to another polynomial, depending upon the coefficient of the largest, the largest coefficient, largest exponent. The other thing that we're going to define is we're not going to think about polynomials as having a fixed width. In other words, with an 8-bit number, you might say that, that this, right? you might think of 7 as an 8-bit number, right? It's got a bunch of zeros, but we're not going to do that in polynomial math. We're going to think of 7 as a 3-bit number. Right? Okay, that's where 7 is not this, but a 7 is that. Okay. And then now, given the fact that we don't ever store or propagate high-level zeros, we're going to define the width of a polynomial as the position of the bit number, okay, of the largest. So the width of 7 is 2, because it is x sub 2 plus x sub 1 plus x sub 0, right? That's what a 7 is. 7 is this polynomial, and so therefore its width is 2. Okay. So this is an actual CRC polynomial, right? What's its width? Nope. It's the position of the highest bit 1. Okay. Which of these is highest? 16.
16.
Yeah. So its width is 16. So if you want, you could say it's whatever it is, -1, you know, whatever, you know, but it's the width of this polynomial. So when we see a CRC, when we see a CRC 16, then it was the W equals 16. The polynomial is actually 17 bits wide. And often this bit is implied, okay, and not actually stored. But we'll get to that in a moment. All right. So the width of a polynomial is the bit value of the largest coefficient, I mean, the one with the highest exponent. Okay, so now, okay, so this is where, okay, let's see. We're going to do division, but we're going to do it in polymath. Remember, we're going to do it in math, which is, yeah, which is when I do a comparison, I'm going to do a polynomial comparison, and when I do a subtraction, I'm going to do a polynomial subtraction or an XOR. Okay. This is the polynomial, right? See the polynomial right here. It's got width 4. Okay. And when I'm done, this polynomial, which is, you know, this 5 bits wide, but W is 4, is going to end up with a remainder, which is exactly 4 bits. And this remainder is going to be my checksum, right? So that's the thing I'm going to append to my, that's the thing I'm going to append to my message for error detection. All right, so let's, okay, I'll go one more. I quit this one, discard. And then I go to the next slide. Okay, next slide. All right, okay, so now since I want to type, no, back a little bit. All right. Okay, this. All right. So okay, actually it's the next slide. Okay, so this one. Yeah. All right, so the first thing I'm going to do when I go to do the division is to pad the end of my message. Again, this guy here is the message, this blue one. That's my message. It's an 8-bit message with a 4-wide polynomial generator. It's called the generator. And this is my generator polynomial right there, which is going to be this guy here that I'm subtracting. Okay. So the first thing I'm going to do is to add 4 zeros at the end. Okay, it's the first thing I'm going to do. Okay, so I do believe. And so now I am going to take this guy here, right? And stick it right here and ask the question, right? Is it bigger or not bigger, right? Which is bigger, the blue one or the black one? I shifted it
The
over.
black one.
The black one's bigger, okay? So I am going to very carefully put in a 0 there, okay? And not subtract it, because that would be wrong, right? Because I'm only going to subtract if it's bigger, okay? If the dividend is bigger than the shifted divisor, okay? And then I take this guy. Yeah, come on, come on, come on. There we go. Okay. And just like I did before, every time I do one, I lose a bit. Okay. I'm guaranteed for that bit to go away. Okay. I'm just am. Okay. So I'm going to take this guy here, stick it in there. And now, which is bigger, the dividend or the shifted divisor? This blue one here or that black one? Which one's bigger?
The blue one.
The blue one. So I'm going to add a bit in my quotient and actually do the subtraction. Okay. All right. So now this is actually easier than regular subtraction, is because I don't have to do any carries, right? I can do it left or right. So that's going to be a 1. That's going to be a 0. That's going to be a 1. That's going to be a 0. And then the other bits are copied. Okay. Because I just did it bitwise, exclusive OR, I hope. Okay. All right. And I'll do the same thing again. All right. Which one's bigger? You can't tell me? You can't tell me? No, 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 no. That's you can't actually tell me. Okay. But when I did these, I could tell the dividend was smaller. But when I have really two choices. Is the dividend smaller, in which case I don't subtract, or are they equal, in case I equal or greater, in which case I do subtract. Okay. So these guys here are actually equal in polynomial size. I don't know which one's bigger. I am going to subtract them because the dividend is not less than the divisor. Okay. Just warning you. Yeah.
Wait,
so-
I'm confused why they're equal.
But they're not greater than, because there's no place value here. This is not place value. When you
Oh, so you're just
compare-
doing literally the number of ones?
No, I'm doing the position of the largest one.
Oh, the position of the largest one? Okay, so then that
Yeah.
last one was equal too, right?
Yes, they were all equal, but
Okay.
when I misspoke the last time, you were going to not subtract when the dividend is smaller. You are going to subtract when the dividend is not smaller.
Okay.
But not smaller doesn't mean greater than or equal to. Well, I guess it does. So I am going to not subtract when the dividend is smaller than the shifted divisor. I am going to subtract when the dividend is not smaller. Okay. So these two, this is not smaller than that. This is not smaller than that, so I am going to subtract, which again is exclusive OR. Yeah, I got another one. And again, I always lose the top bit. Okay. All right, so this is an example where I know the dividend is smaller. right? Because the position of the highest position of the 1 is more to the right than the highest position of the 1 in the shifted divisor. So I am not going to subtract. Okay, so I skipped a 1 over here, and I'll get a 0. Okay, I'm not going to. So again, no subtract, 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 no subtract. And again, it's just as one. Okay. And again, I always lose the top bit. Okay. Now the dividend is not smaller, so I am going to subtract. And 0, 1, 0. I'm doing exclusive OR, bit exclusive OR. And I always lose the top bit. In other words, I'm always making progress. Right? That's the yeah, obviously. And then again, the dividend is not smaller. Okay. I mean, I know in your mind it looks like it is smaller, but it isn't. It's not smaller. The position of the 1s is the highest position of the 1s is equal. So it's not smaller. Okay? So I am going to subtract. Again, I throw away the top bit. 0, 0, 1, 0, 0. Okay, good. One more. I compare. I'm not going to subtract. And my remainder is going to be 0, 4, 0, 0. Okay. My remainder is going to be a 4. I don't know what my quotient is, whatever that is. I don't care what the quotient is. The remainder is the cool part. Okay. Just in case I totally messed up. Just in case I totally messed up. There it is, all worked out. Yeah, I don't know if I did exactly. Yeah, it's just pretty much the same. Yeah. Okay. Again, I don't care about the quotient. I only care about the remainder. I'm going to take the original message up here in blue. I'm going to concatenate it with the remainder. And I took an 8-bit message, created a 12-bit. I took an 8-bit data, added 4 bits to it to get a 12-bit message, and I sent that message. And the whole point is it's very chaotic. If you look at the correlation of each bit in the remainder versus each bit in the message, it is very chaotic. And the way I'm going to, this is how I'm going to generate it. I'm going to check it the same way I generate it and just make sure I get the same remainder, right? Because everyone, you have to agree on the polynomial. And this is a 4-bit polynomial. You have to agree on the polynomial. And both on the side, you have the width, the polynomial, all of that you have to agree on. You have to agree on the order of the bits. This is a forward calculating from most significant to least significant. Most actual protocols are reversed because, I don't know, back in the UART days, the bit 0 came first. And so the original protocols back in the 60s reversed the bits because the UART reversed the bits. You probably got that question wrong on the 319K final. But this is not, this is a forward protocol. So embedded in here is, so let's, before I get to the code, which I'll probably do next time, let's review what it is I did. Okay, so the message is completely arbitrary. Okay, you got that. This could be any. This could be any 8-bit value. Okay, it was just representative for me doing this math. the polynomial is a constant, okay, that both sides agree on. What happens as this polynomial gets bigger? If I add more bits to the polynomial, well, in what way is it better? What's your intuition? Something's going to be better and something's going to be worse. Okay. Let's just look at W, the ratio, right? I took an 8-bit message and I added a 4-bit checksum or 4-bit CRC with the polynomial equal to 1/3 hex.
I would have a larger remainder, which might encode more information.
No, there's no information in the remainder. So the information is in the message. So you might have meant this, you might have meant it correctly, but you didn't say it correctly. So what is the intuition here? As my polynomial gets bigger, what gets better?
Error
Yeah,
detection.
the error detection rate, the probability of detecting an error. My Hammond distance will increase. All right, so if I take an 8-bit message and I have an 8-bit CRC, I need more bits to flip in order for it to be undetected, okay? So if I add more bits to my polynomial, my chances of detecting an error will get better, okay? Well, what gets worse?
More bits for just more bit being wasted instead of using in the message.
Yeah, see, so I sent, in this case, I sent 4 bits just for the purpose of detecting errors. So if I go to 8, so the term I'm looking for is the bit rate, okay? As I increase the polynomial, the bit rate of this protocol will go down because I have to send all the bits, but only some of them have data, right? So in the context of my system, I have n bits of message plus w bits of checksum, and then I will going to n divided by is going to give me a ratio of the cost of adding the checksum. Okay. Now, if n is 10,000 and w is, if n is 10,000 and w is 16 or 32, okay, that cost is very small, right? That cost is very small. So that's why we do it. What happens as the message, when W gets bigger, when W gets bigger, the probability of detecting an error gets better, goes up. Probability of detecting an error goes better, and the probability of missing an error goes down. What about when n goes bigger? What happens as n gets larger? Can you see what? Can you get a sense of what would happen?
It would as if W gets smaller. It's like the opposite, I think.
Yeah. See, so the ratio of n and w is the parameter that lets us assess the probability of error. Okay. As n gets larger, the undetected error gets worse. Okay. And so you'll find that the size of this polynomial is is, okay, I'm going to show you one more slide and then I'm going to come back to this one. Okay, I want to quit. I first want to do is I want to save any of this crap. Do I? No, I'm going to copy this. No, copy this. Then I'm going to discard. Oops. No. Reset. Okay, info. Okay, but I'm going to close it, not save it, open it back up again. As it gets bigger. Okay, so I want to show you one last thing before, which is sort of the last slide of the whole thing, just to give you a perspective of where we're going with this. We've done all the crappy math, not crappy, but the fun math. Okay. All right, I'm going to save that now. Star. This is where I left off. Save. Okay, so. Just want to, we'll revisit this table at the end when we get to that slide. But okay, so this are a whole bunch of codes. This one has got special, the 1-bit wide code is actually this polynomial here. And yeah, I'll show that to you when we get there. But you see, as the bits get larger, you see this? As the bits, as more and more, as W gets larger and larger and larger, there are a lot of protocols and a lot of people in this space designing new protocols and telling you that all the existing protocols, these are all standards, by the way, standard protocols. And as you might imagine, the bigger the CRC, the larger the Hamming distance. So we'll see over in this guy here that as you increase the number of bits, the Hamming distance gets better. Okay. Anyway, so the point that the point I wanted to show you in this table is there's a lot of W's out there. Okay. The W is the W can vary a lot, and the polynomials can vary a lot. Okay. Okay. So what we're going to do next time is just show you some C code that gets faster and faster and faster, that implements it, and then we'll go on back to Wi-Fi. And so I'll let you stew this part of the lecture to see if you have any questions, and we'll do them next time. Okay. All right. Stop sharing. Just to remind you, the most important thing we did was width and chaos. Okay. Those were the two fundamental principles of creating a checksum. Okay. And width is the thing which tells you how many extra bits we're going to add, and chaos really tells you how many bits do I have to flip, what the probability of randomly flipping bits and ending up with an undetected error. Okay, so this whole CRC approach was designed to be chaotic and have large Hamming distances. All right. Okay, so stop recording. Questions? Those of you who didn't come right at the beginning, I will grade the tests. I haven't yet, but I will.